will speak on polynomial invariants of elliptic reflection groups.
Okay, thank you. So I'm glad to say that Ole has arrived because we were in danger of violating the fundamental rule of special functions conferences that there has to be at least one Dutchman present. So,
You're welcome there.
anyway, well, as it says here, this is on the archive. The title is kind of different on the archive because I was focused on sort of the general algebraic geometry of things. But in the end, it's all about it really is about elliptic curves in the end. So I figured for this conference I would make a slightly different title. And the reflection groups we've actually seen already. This conference, Oleg mentioned them in his Monday morning talk. Where I'm coming at this is there's a very nice fact in invariant theory, which is that if you take a finite group acting on some complex vector space, no microphone. Mind you, I talk loud. Mind you, I talk loud anyway. Okay, this is already, it seems a little bit loud, so.
It's okay.
Okay.
That's good.
All right. So, in general, if you have a finite group acting in a complex vector space, it acts on the ring of polynomials, and you can look at the ring of invariants, and it's almost always horribly complicated. I mean, there's some general facts like it's Gorenstein, or it's Macaulay, et cetera, but in general, it's very, very complicated. But there are a few classical examples where it's just freely generated by some finite collection of generators. So it's a polynomial ring. And the most classical example of this is a Weyl group acting on the maximal torus of a Lie group. And there, basically, you get nice polynomial invariants. And there's a generalization of this due to Shepard and Todd, basically, who have a very bad proof of the fact, and then Chevrolet came up with a very nice proof of the fact, that basically this actually works for a bigger class of groups called complex reflection groups. And so a complex reflection is an element of GLN such that if you subtract 1, it has rank 1. So in other words, given that we're dealing with finite groups, it has finite order, it has one non-trivial eigenvalue with multiplicity 1. Okay. And so the theorem, so Shepard and Todd basically just said, okay, here is a complete list of all the complex reflection groups, and then they computed in every single case that the polynomial ring was invariant. And if the invariant ring was polynomial, Chevrolet gave a nice if and only if proof without using sort of any classification anywhere. So and I should confess here that I'm definitely following the Shepard and Todd tradition, not the Chevrolet tradition. The generalization I'll be telling you about. Okay. Now, there's a generalization of this, and this actually is like the one place where I sort of touched lightly on the actual name of the conference, because there's a representation theoretic version of this statement about Weyl groups. Namely, if you have a Weyl group acting on the maximal torus, not the Cartan algebra, but the maximal torus, the invariants are still a polynomial ring, and that invariant ring is just the character ring of the group. So that's completely familiar. And it's generated by the fundamental invariants. Now you have to be a little careful because you have to take the correct isogeny class of the group. It needs to be either simply connected or adjoint, I forget which, but otherwise it's not quite polynomial. But if you do the right thing, it's still polynomial. And there's a nice version of this for elliptic curves where you replace basically the multiplicative group by an elliptic curve. You can do that, and what you find essentially is that if you take your elliptic curve, you tensor it with the root lattice, and then look at the invariant theta functions on that abelian variety. That is a polynomial, again a polynomial ring. This was either proved or conjectured by Louis Enge de Behan, who you asked, and then proved by Bernstein and Schwarzman, if you asked them, or Louis Enge if you asked. So basically, Louis Enge certainly very solidly computed the invariant space and proved that it had the same Hilbert series as a polynomial ring. And then the only question is whether he actually proved that it was an invariant, a polynomial ring or not. But okay, anyway. And Bernstein and Schwarzman actually give a converse statement, which is that if you have a finite group acting on an abelian variety, and it has a ring of theta, and it has a multiplier or a line bundle such that the corresponding ring, the theta functions has polynomial invariants, then that group has to be the analog of a reflection group. Namely, every element has, so you have generators that fix hypersurfaces in this abelian variety. It also has to be irreducible, and this is basically, and you can sort of kind of basically see this just by saying, yes, we're saying that the quotient is a weighted projective space. Well, if you take a product of two things such that the quotient is a weighted projective space, then the quotient is going to be a product of weighted projective spaces, and that's not a weighted projective space. So that's so there's an irreducibility constraint. And also, just as with the torus, you need to choose. It's not just every abelian variety in which it acts. You have to choose the class, the representative of the isogeny class carefully. Okay. So, right. And as I said, they show the if statement when it's in the Weil group. And I'm getting tired of not being able to see what I'm doing. So let me very briefly switch to mirroring. Okay, and now I need to actually get back to the thing I want and not like the manual for the pointer that wasn't working. There you go. Alright. And now I can see what I'm doing. Woohoo! Okay, so, right. So they have this nice conjecture. Now, where I come into this picture is, this is actually something I was talking about at the last conference in Stockholm. I was talking about elliptic, double F, and Heck algebras, whatever they are. And these are attached in general to a Weil group, acting on an abelian variety. And in order to deal with these spherical algebras of these weird objects, and show that they behave well, I need to know that the quotient of these abelian varieties by these Weil groups behave well. And so I needed to prove flatness of the invariants. And I'm the sort of person who wants to do things over Z, not just over C, so I want to get flatness in an arbitrary characteristic. And what I found is that indeed, I could show by using various results that are basically, well, among which are several results that I think Hjalmar and Michael Schlosser had come up with for sort of summing over Weil groups and getting nice constants as sums over Weil groups. I was able to prove that the dimension doesn't depend on the characteristic. And so in particular, even in finite characteristic, and the weird thing is that this is true even when you divide the order of the group. And there's always bad characteristics for the sort of more traditional cases. But even when you divide the order of the group, you still have flatness. And so in particular, it has the same Hilbert series as a polynomial ring. And so this suggests, but it definitely does not imply, in fact, if you look at the paper, I'm not going to give these specific examples, but if you look at the paper or write this up, there are examples of quotients by reflection groups that are not polynomial rings, but have the same Hilbert series as a polynomial ring. So you do have to be careful. Okay, now, just to sort of mention where you might see Weil group actions showing up, is, well, okay, so AN or CN are pretty popular. There's lots of papers out there about AN invariant hypergeometric, elliptic hypergeometric things, and CN invariant elliptic hypergeometric things. Also, if you look at these sort of terminating elliptic hypergeometric sums, both the univariate cases and the Selbergy cases, those have an E6 symmetry. And then there's also an E7 symmetry in the picture, but I don't know how to get theta functions out of those, so we'll just ignore that. And then, as I mentioned, for the application, I had these double F and Heck algebras, and I needed to know that the spherical algebras were flat. Okay. There's another place where this came up is I was doing some non-commutative geometry stuff, where basically graded algebras non-commutative algebras deforming the homogeneous coordinate rings of delta surfaces. And what I found is you can sort of build in, okay, there's an elliptic curve at infinity with some Q deformation. And you just ask sort of, okay, given that I have this thing at infinity, what are the possible ways of extending it to something two-dimensional? And what I found is using the geometry of non-commutative delta surfaces, I could actually describe all of these moduli spaces as quotients of abelian varieties by Weil groups. And so using these known invariant theory things, I could actually say, yes, this invariant, these are classified by weighted projective space. Now the thing is that, at least for the commutative case, this works perfectly fine in finite characteristic, and works in reverse. Because basically, there are other ways of computing these moduli spaces just by saying, hey, I'm taking the Weierstrass equation of my curve and adding low degree coefficients. We'll see an example later. And you can just say, okay, well, these are the generators. And thus you get a direct proof that, even the 6 mod Weil group of E6, say, is a polynomial ring. And that works in arbitrary characteristics. And so basically, once I realized this, I was thinking, okay, well, there should be ways of pushing this to other cases. Which cases of the Bernstein-Schwarzman conjecture can I actually prove in finite characteristic? And so I was basically just thinking, I'll get a lot of support for the conjecture, prove a lot of special cases, and then I kind of forgot to stop proving special cases. So ended up with a theorem. Okay, so in particular, so I'm not just trying to prove Bernstein-Schwarzman's conjecture. I'm trying to prove something in finite that includes finite characteristic. And what this means is I can no longer use sort of analytic techniques that Louis-Enge and Bernstein-Schwarzman used. I have to use algebraic or geometric techniques. Now the plus side is this means that in the end, I'm able to do computations using Grosvenor bases to deal with some of the hard cases. So it does make something nicer. Okay. Now already there's an obstruction in coming up with the analog of their conjecture, because they actually basically say, okay, the action of the universal cover should be crystallographic, should be generated by reflections, and there really isn't a good universal cover in the algebraic set. But the universal cover is, of course, the universal cover, and it has all these finite covers inside, lying under it. And it turns out you can actually rephrase their condition as a condition on every single intermediate cover. And then those are actually isogenies, and isogenies make sense in finite characteristic. So even though they're no longer covering spaces, you can still talk about the set of all the intermediate covers in finite characteristic. And so you basically have a condition that says, okay, let me define a reflection in complete generality. If you have a variety, and you have an automorphism of that variety, it's a reflection if and only if its fixed locus contains a hypersurface. Okay. And so, and then a reflection group acting on a variety is one that's generated by reflections. And so there's a notion of a crystallographic action, which is basically that if you take any G-equivariant covering, isogenious abelian variety, and then look at how the kernel of that covering, it comes to the homomorphism of abelian variety. You look at the kernel that has an extension by the group G that acts on A prime, and should be generated by reflections. Okay. So, and then it turns out this is now an infinite number of conditions, but it turns out actually there's one cover that suffices to check, and if it works there, it works everywhere. So, okay. And so then the main result is, I'll give the complex version where there aren't annoying counterexamples. If the group acts on the complex abelian variety as an irreducible crystallographic reflection group, then the quotient is a weighted projective space. Moreover, as long as your abelian variety has good reduction to characteristic P, even if P divides the order of G, this is going to remain true for the reduction. Okay. There's a slightly broader version of this statement, which does not ask for lifting the finite characteristic. It says it's crystallographic and acts by it's in general, if you have a crystallographic reflection group acting on a abelian variety, then it almost always has a polynomial invariance, but there's like 5 cases where it fails. And I don't have a good characterization of those 5 cases, but so basically there's a huge number of interesting cases where it still works, including all the infinite variables. Okay, so how can one prove this? Well, okay, as I said, I'm following the Shepard and Todd approach. So the first step is to classify everything. And so in particular, the first question is sort of, how do you classify reflections? And the problem is that we have these translations involved, possibly. So when you talk about a reflection, well, it turns out every automorphism of the abelian variety that does not fix the identity, you can translate to something that does fix the identity and is canonical. And if it's a reflection, and this reflection basically is your reflection if and only if the translate that fixes the identity is a reflection and you fix some point. So reflections basically boil down to things that fix the identity. And if you fix the identity, then, well, when you subtract 1, it's essentially rank 1. The image is going to be a one-dimensional abelian variety, also known as an elliptic curve. And so, because of your reducibility, these image elliptic curves coming from all of these different reflections, these root curves, if you will, are basically going to generate A. And so, if you pick a suitable set of n of them, it's going to give you an isogeny. And so you're always going to be isogenous to a power of an elliptic curve. And the anamorphism ring of e to the n is just basically the matrices over the anamorphism ring of E. And so it's going to be matrices over either Z, if it's a general elliptic curve, an order in a quadratic field, an imaginary quadratic field, if it's a complex multiplication curve, or if it's a supersingular curve and finite characteristic, it can be a quaternion algebra. But basically, this matrix algebra is very simple, and the isogeny is just basically saying, okay, well, I'm allowing some denominators and forcing some congruence conditions, and that'll give you the anamorphism ring of A, and so on. So the upshot is that any crystallographic reflection group acting on an abelian variety is going to give rise to a real complex or quaternionic reflection group acting in GLN of the appropriate algebra. Okay. In the complex case, this was classified by Popov. There's some papers that claim that this classification is missing. Some cases don't believe them. Is actually correct. I directly checked that, yes, the case they claimed was missing was not missing. But the problem is that he's assuming the complex case. And a priori, there could be interesting cases that involve isogenies that are still complex but don't lift a characteristic 0. And indeed, there is one case that only works in characteristic 2. So I did this giant calculation to redo their Pavlov's calculation to find exactly one missing case. But, it is what it is. But of course, also you need to do the quaternionic case if you want to be as complete as possible. So there's a bunch of quaternionic cases. There, sort of the annoying part is just classifying all the quaternionic reflection groups that fix the identity, and then the lattice question is not so bad. Okay. But in any case, you get a finite list of groups plus some infinite families. Now, so this is basically an issue. So we have this classification. So now all we have to do is, in every single case in the classification, compute the invariants. Now there are two problems. First is there are infinite families. So and I often find that the infinite families are the hard case because you just can't just ask the computer. However, there's also the case that the sporadic cases that are left over after you remove the infinite families can be really big. This is, 39 million elements of this group, and it's acting on a 6-dimensional abelian variety. And, well, once you have to do the calculation, you find that the largest invariant has degree 12, and the number of sections of that line bundle that contain this guy is 2.9 million. So even just writing the thing down looks annoyingly hard. So so it's not, you can't just ask the computer, because basically in order to find the invariants, you'd be doing linear algebra in this 2.9 million dimensional space if you try to do things directly, and that's assuming even that you can write down the invariants directly. But the problem is this an abelian variety. It's just given to you as an abelian variety that's isogenous to e to the 6. So you actually need to start with a bigger space. Cut it down by modding out by some translations, but then it's hard to see how the group acts. So there's a lot of issues. And in this case, I will admit I cannot do it in any nice conceptual way. I have to ask the computer. But once I accumulated enough tricks, I was able to do at least the characteristic 0 case in 1.08 seconds. So it is in fact eventually a doable calculation, but you have to do some tricks. This is the hardest case. Okay. No, so the infinite families, well, there's two sets of infinite families. One of them is the symmetric group, which we'll see is basically trivial. The other one is these imprimitive groups that the complex cases of that were sort of the focus of Talek's talk. Which is basically you have, the simplest cases are you just have a group acting on an elliptic curve, and you take the wreath product with Sn. Now this is really easy to understand the invariance of, because you have this giant normal subgroup g to the n that you can mod out by, and then turns your e to the n into p1 to the n. And now you take p1 to the n and mod out by Sn, well that's just a projective space. And in fact, we know the basis is just basically your favorite basis of essentially the elementary symmetric complex. Now, we can actually extend this a little bit. G doesn't have to actually doesn't have to fix the identity. You can throw translations in and do the same sort of picture. And moreover, then once you do that, you find that at least all of the infinite families either come from this sort of wreath product or from a relatively simply described normal subgroup of the wreath product. Which means that you can describe all of the quotients as small abelian extensions of Pn. And you can then get enough control over the things you're taking roots of to show that in fact the roots of the generators are in fact basically can be thought of as generators, and so you get a way to projective space. And you see the same same sort of 2, 3, 6 or 2, 4, 4 that Oleg was seeing in the complex cases. Now, this n greater than 2 is slightly annoying. There are weirder things you can do for n equals 2, but there's only finitely many of them, so we can pretend that they're sporadic. But the other thing is that they're always acting, you can always think of them as acting on e squared. And we can write down invariant theta functions on e squared. They're just basically homogeneous polynomials and y and x. So they're very easy to write down. And so you can just, and figure, moreover, it turns out that there's always a diagonal plus minus 1 acting, so it really reduces to a reflection group acting on P1 cross P1. And yeah, that's basically just some finite subgroups of SO4. So they're all easy to do. Okay, and I mentioned the other infinite family is, well, in that case, there's a unique choice in the isogeny class. It's the sum 0 subvariety of e to the n. And Sn, also known as an minus 1, acts on that. But the quotient is, well, you're taking this ordered n-tuple of points that add to 0 and turning it into an unordered n-tuple of points that add to 0, also known as a divisor that adds to 0. And divisors that add to 0 are just within your system. So all you're doing is you're taking this line bundle of degree n, of course, and looking at all the sections of that. And every section of that has a it vanishes precisely on n points that add to 0 with multiplicity. And conversely, for any n points that add to 0, there's a unique section of that line bundle. And so it's a projective space. This is the other nice case where you get a projective space, other than these semi-direct, these wreath products. Okay, so that's all the infinite cases out of the way. What about the sporadic cases? So these are all primitive groups. And and the annoying issue about the primitive groups is that we can no longer think of them as acting on the sort of product form of e to the n. They're acting on things that are e to the n or isogenousous to e to the n, but the polarization is different. The line bundle is not the obvious, just take degree 1 in each coordinate. So this means that it's a lot harder to, just writing down these sections gets harder. So we have to use some tricks. The first trick is really nice, really conceptual, and it's what I alluded to earlier, which is that, well, okay, sometimes A mod G is actually a moduli space of classifying certain nice geometric objects, and we can compute that moduli space in other ways and see that it's a way to project the space. So that's good. Another approach that works in quite a few cases is that these groups often have normal subgroups that we can understand the quotient by. And so if we can compute the quotient by the normal subgroup, and the quotient of the group by the normal subgroup isn't too bad, then we can figure out what's going on. Okay, and then the final trick, this is one place where the fact that I want to work in finite characteristic is actually a win, is that there's a way to induct through a crystallographic subgroup. But to do it efficiently, you need to be able to generate random points that are related by the big group. And that works really well over a finite field, really badly in characteristic 0. Okay. So let me talk about the geometric approach. So this turns out to be, oddly enough, actually means that other than the AN case, the next easiest, well, I guess the primitive cases aren't too bad, but the exceptional cases are actually in some ways easier than the primitive cases. The E6, E7, and E8 are easier. And so let me talk about E6. So as everybody knows, well, okay, everybody, which may not include everybody in this audience, but as every algebraic geometer knows, a cubic surface in P3 has 27 lines on it. And what slightly fewer people know, but should know, is that there's an action of the Bob group of E6 on those 27 lines. And what even fewer people know, but should know, is that if you look at those lines as divisors on that rational surface, they satisfy linear relations. And if you quotient out by those linear relations, you essentially get the lattice E6. Now what this ends up meaning is that if you have a cubic surface and you pick a hyperplane section and choose with an isomorphic to some fixed elliptic curve, I mean in general this is some smooth genus 1 curve. So it's fix an elliptic curve and an isomorphism with some hyperplane section of your cubic surface. And then you ask how those 27 lines meet that elliptic curve. That gives you a map from the dual of the root lattice to E. Or in other words, a point in the tensor product of E with the root lattice. But because of the action of the Bob group on the lines, what it really gives you is an element of the quotient. And conversely, it turns out that you can, given a point in that quotient, you can choose a point in the pre-image and use that to determine a cubic surface with a labeling of the lines, canonically. And so the moduli space of cubic surfaces with a hyperplane section isomorphic to E can be canonically identified with precisely this quotient that we want to understand. Okay. And so, but moreover, you can write down cubic surfaces like that. Because, well, okay, so let me take the affine patch that's complementary to E. Just to make it sort of clearer. So what we have is well, okay, in the biggest degree, in leading degree, we have the equation of E. Because that's basically setting 1 equal to 0 in this affine patch. So we get the equation of E. And then we're adding lower degree terms to get an actual cubic, to get an affine cubic surface. But, well, you can add a constant to Y and a constant to X and a constant to Z. And by doing so, you can eliminate 3 of these coordinates, A1, B1, adding a constant to X eliminates A1, adding a constant to Y eliminates F1, adding a constant to Z eliminates B1. So you eliminate 3 of these things. And so you're left with 3 things of degree 1, 3 things of degree 2, 1 thing of degree 3. Now, those who are familiar with the affine Bob group will recognize as these are the standard labels in the affine Dinkin diagram. This is in general a theorem basically because of this is what Louis Enga sort of basically proved, is that you have the same Hilbert series as the polynomial ring with the invariants coming from the labels of the Dinkin diagram. And I should say I do not have a uniform description of what the generating degrees are in the complex case. Okay. And this is sort of, I'm being lazy here and working, dividing by 6, but you don't have to, you can make everything work. Okay. And then you can do something similar for E7 and E6 using other Del Pezzo surfaces. And moreover, you can get some other groups into the picture by saying, okay, let me take an automorphism of E and ask for that to extend to the surface as an automorphism of the surface. And so now again, you're basically taking the formula for the automorphism and adding lower degree terms and asking for consistency. And so you can again do the same kind of just solve for coefficients thing to figure out what the moduli space is. And on the other hand, you can figure out, well, okay, I'm asking for elliptic surfaces that are invariant, that are fixed by some element of the Bob group. And what you find once you sort of trace everything through is that, for instance, if you take the cubic surface case and ask for it to be preserved, ask for the translation by a 3 torsion point on E to extend, what you get are the invariants corresponding to G2. And similarly, if you do this for F4, if you take a 2 torsion point on the E7 surface and ask for that to extend, you get the invariants for F4. And so if you've been keeping track, well, that's now all of the Lie groups. I told a slight lie, there's a couple of isogeny classes for G4 and F. G2F4, but you can do this by other extensions of isomorphisms. The other thing you can do is you can take the E8 case, and if your elliptic curve has additional automorphisms as an elliptic curve, like if j equals 0 or j equals 17 or 28, again, what Oleg was talking about, then you can ask for those to extend. And what that's going to give you, because you're basically asking for square root of minus 3 to extend to your surface, that ends up basically extending the square root of minus 3 to your moduli space. And so now you get a quotient of e to the 4 by a complex reflection group. And then you can do some, if you're really masochistic like me, you can look at the cases where j is both 0 and 1728, which of course means the 2 or 3 is 0. So characteristic 2 or 3. And there you can ask, there the automorphism group is basically the unit group in a quaternion algebra, and you can ask for that to extend to the surface, and you get a couple of quaternionic reflection group cases in that way. Okay. So that exhausts the cases where I can actually explain what this quotient actually means. So now we're in a much more ad hoc, or less, some things that tend to require some amount of computation. So as I said, we can ask for a normal subgrid that works reasonably well. And so the basic idea would be, you take the quotient by the normal subgroup, and either the quotient is a simple enough thing that you can ignore the equations that it might satisfy, and just do normal invariant theory to figure out, normal polynomial invariant theory to figure out what's going on. And then hope that there aren't any additional invariants in finite characteristic. And in particular, there's one family where the quotient by n is a polynomial, is a weighted projective space, because it turns out n is already is itself a reflection group. That's not so many, and they're only quaternionic, but it's like 3 or 4 cases, I think, that come up that way. The other one is that there are some cases where n is big enough that the quotient is a hypersurface. At which case then, well, okay, there's only one invariant. You're quoting by something which is invariant of the group. And so it's not unreasonable to expect that extends to a generating set for the ring of invariants of the actual finite group G mod n, which won't be polynomial typically, but you can still hope to sort of control it well enough. And that indeed works. Luckily, Magma is perfectly happy to tell you, yes, these are the polynomial invariants of this finite group. Okay. And, right. Okay. Now, the other thing that happens, this overlaps a little bit, but basically, if the subgroup is -1, well, this is the type of quotient that has been very well studied. Abelian varieties mod plus -1 are called Kummer varieties, and there's lots of literature on them. In particular, we know a fair bit about, how far up you need to go to generate their homogeneous coordinate rings or things like that. And so you can actually, in many cases, compute generators of the Kummer. But also in low-dimensional cases, we know what the Kummers look like. Abelian varieties, principally polarized abelian varieties of dimension 2 or 3 are Jacobians. And we know, we know how to compute the Kummer varieties of Jacobians without too much difficulty. And so you can actually just directly figure out, okay, here's how the group is acting on the Kummer variety of this curve. For instance, for one of these weird cases where the imaginary quadratic field there is square root of -7, C turns out to be the Klein quartic curve, which has 168 automorphisms. And you can tell that because it's the only curve with that many automorphisms. And so you so you can just write down the Kummer variety, look at how G mod plus -1 acts on that, and compute the invariants. And then do a little bit of fussing about to argue about the fact that, well, that's not actually a polynomial ring because it's not the right line model. But you can basically say, well, okay, it satisfies this nice relation, which turns out to basically be along the lines of a squared equals b times c, and so if you join the square root of c, it becomes a polynomial ring. Okay. But this only works in low dimension. Because, we really don't know what abelian varieties in dimension 6 look like, even if they're principally polarized. And even in dimension 5, where we have some idea what they look like, well, the description we have isn't actually canonical, and so there tends to be multiple ways of describing it, which does not work well with groups. Okay, so we do one more approach. And so this is a very general approach with a caveat. So the basic idea is we choose a non-normal subgroup for which we can understand the invariance. And well, okay, by induction, we know this for crystallographic reflection groups. Okay, and then we have this nice little lemma, which is that, okay, if you have a function on the abelian variety, which is invariant of the subgroup, then it's invariant of the big group if and only if, for every point of the abelian variety and every element of the group, it's invariant. This is mostly trivial, but you know, you have to go over the algebraic closure in principle. But here's the thing. This means that for any point x and g, for any pair x and g, we get an equation. So we can either take, and in particular, you know, it's enough to take g to be something that generates capital G over capital H. And so in particular, we can take x to be, we can get random equations by taking x to be random. And then we can hope to be lucky, and then if we've generated, you know, more equations than we think we need, then they'll actually be linearly independent and actually cut out the right space. Okay. Now, of course, there's a caveat there, which is that we're hoping to get lucky, and we can convince ourselves the probability is really, 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 really small. But I want to prove. So how do we deal with that? Well, okay. So here again, we sort of get into some representation theory. We know a lot about how groups act on sections of line bundles on abelian varieties. There's this Heisenberg group acting by the translations, the kernel of the polarization, and then our group is going to be acting on top of that. So we have this nice group that we in principle understand. And there are certain cases where in principle means this turns into something very simple like, okay, in some vector space over a finite field, how many fixed points does a group have? Which is something extremely easy to compute, because it basically for each conjugacy class is just asking about the rank of G minus 1 on that finite field. And so there are a number of degrees where we can directly compute the number of invariants in characteristic 0. And for instance, in the ST34 case, we can't do it in degree 12, but we can do it in degree 13. And degree 13, we know exactly how many invariants it's supposed to have. And luckily, it turns out to be exactly the same as what we expect in the polynomial ring. And that is, and that formula for characteristic 0 is a lower bound of any characteristic, just by semi-continuity. And so on the one hand, we have this space, which is guaranteed to contain the space of invariants of that degree. And we have a lower bound on the dimension of the actual space of invariants. So once the dimension of the space we get, once it has the correct dimension, it's the correct space. And then once we've written down invariants of degree 13, it's then not too hard to sort of peel off, okay, here's an invariant of degree 1, here's an invariant of degree 2, which is independent of that, and so forth, and get a putative set of generating invariants. And then you just check, are they algebraically independent, which is a Grobnier basis calculation. And once you've checked that they're algebraically independent, well, we know the degree of the quotient variety. And so if it has the same degree as this weighted projective space that we think we have this putative weighted projective space, which has a rational map from our actual quotient, by just forgetting some invariants. If it has the right degree, it's the right quotient. Okay, and so then, now there is a small issue. You know, I'm talking about taking random points, and if you take random points in characteristic 0, there's this issue where basically addition on abelian varieties in characteristic 0, the number of bits you need to write down points grows quadratically as you start adding things, and so you don't want to do that. So basically, what you can do is, again by a semi-continuity argument, if it's true in some good finite characteristic, not defining the order of the group, then it's true in characteristic 0. And so basically the way I deal with ST34 is I work in characteristic, I think 11, which is the smallest good characteristic, work over a big extension of F11, take random points there, use the Galois group to actually get multiple equations out of every random point, and then solve the equations to get the invariants and say, hey, I'm done. Now, this doesn't give me the full theorem because I want to prove an arbitrary characteristic, But what it turns out is that the one case where your points don't get more complicated as you do arithmetic is torsion points. And you can, by working over a suitable number field, you have enough 4 torsion points on this abelian variety. And you can see that you can figure out how the group acts on the 4 torsion points. And then ask for functions which are invariant under the action of the group, invariant on orbits, constant on orbits. And again, you can solve those equations. And then you just check that, and then you just need to do the coordinate basis calculation and check that it works in arbitrary characteristic. That's actually, that turns out to be the hard part. Well, the 4 torsion orbits and this coordinate basis calculation are the hard part. That takes quite a bit longer than the calculation in characteristic 11. It takes like 30 seconds. So, it's testing the limits of my patience, but it is doable. Okay. So let me now talk about some open problems. The first is the obvious one of, this is not the proof from the book. There should be a proof that directly uses, that just says, hey, this thing is a reflection group, therefore it's polynomial. Why are you classifying these things? Now, there's some definite issues here. If you look at Chevalet's proof, well, you can tell already that Chevalet's proof is not going to give this full theorem, can't possibly give this full theorem, because Chevalet's argument fails in characteristic dividing the order of the group, just because it has to. Because the theorem Chevalet is trying to prove is not true in characteristic dividing the order of the group. But even then, okay, sure, maybe we're happy to just talk about characteristic 0 and get a proof, but it's still, that it is, it's not clear how to do this. Because, at the very least, the fact that it fails in finding characteristic means you either need to do something that's specific to characteristic 0, or you need a proof that's going to work in all characteristics. The other thing is that the statement of the main theorem is not quite the best statement one wants, because I have these 5 specific cases I have to exclude. And okay, 3 of them I can sort of exclude in a principled way. There are quaternionic cases that don't fix the identity, that don't fix the point. And so we can say, okay, maybe there's some reason why that case could be excluded. But then there's 2 characteristic 0 cases, characteristic 2 cases that fix a point, they just randomly don't work. And I don't know why they don't work. But I just basically did the calculation, found independent generators of sort of the degrees you might have expected, but they're not. Sorry, I found generators that look like they're independent up to that degree, and then they don't satisfy equations up to the degree where I actually computed the invariants, but they do satisfy a relation at higher degree, and that actually implies that the invariant ring can't be polynomial. So that's a bit of an issue. In fact, actually, further calculations, at least one of these cases, the invariant ring is not even Cohen-Macaulay. So it's like as bad, it's the worst possible behavior you could expect for invariant rings. Okay. There's another set of open problems, which I think is, my understanding is that there are results on this for the vector space version of the problem, which is, okay, what if we don't ask for it to be a polynomial ring? What if we ask for it to be a hypersurface? So we have one more generator than we thought we needed, but they satisfy a single equation. And my understanding is there's something like this for linear groups, where basically you say, okay, well, they're generated by elements that have, such that if you subtract 1, they have rank 2. So they're sort of almost reflections, but not quite. And there's some results along those lines. I don't know whether one should expect anything like this for elliptic curves. The Bernstein-Schwarzman thing is about fundamental groups, and it sort of very clearly uses the fact that, yes, you're fixing something in codimension 1. I don't see how to generalize that at all. And then, of course, we could ask for something slightly worse than a hypersurface. Maybe it's, has m more 2 more equations than you need, sorry, 2 more variables than you need, but they satisfy precisely 2 equations, or so on. So complete intersections. And then the final open problem, getting back to sort of integrable system-y things, or possibly representation theory things. I'm not sure which one counts as. But I got into this by elliptic double F and Heck algebras. Is there a version of them corresponding to these complex reflection groups? And what I say is not just can you define them? That's probably not too hard, but you actually want to prove that they're flat or things like that as you vary the parameters. And so part of that, this sort of tells you that the spherical algebras behave well, which is a good sign. But you also need to know that for the flatness, in the Weil group case, I basically used the Bruja order on the Weil group, and I don't know an analog of that for complex reflection groups. but there's still some question of, well, maybe we can prove something for the complex reflection groups. And I think for the linear case, there are versions of the Daha for complex and even quaternionic reflection groups. But so where you have differential operators instead of looking difference operators. Anyway, so that's the. No idea what time it is. Oh, okay.
Okay, any questions?
My question is the following. You mentioned E6, E7, E8, this is Y group. In my previous talk, I described algebra 3T3, 3T4, and 3T5. My observation, surprising, that characteristic Poincare polynomials for E, which appears for series E, can be divided by Poincare polynomials of the algebra, which I defined yesterday, and ratio is polynomial. It is a very surprising thing. That means that exponents for algebra which I defined should be some linear combination of exponents for corresponding algebras. And my question is, what happens if I consider 3Tn 6? Is it somehow related with E8 or E10 or so on?
Well, I would expect E9, which is affine E8, but I don't really know. I have a hard time parsing a lot of these funny algebras. Basically, I have a hard time conceptualizing a lot of these algebras, sort of figuring what they mean. So I don't know. I can say completely unrelated to this talk, but I have a paper with Madhav Bazarani where we have similar sorts of results, where basically you have certain representations of the Hecke algebra, of the sort of just classical affine Hecke algebra or affine Hecke algebra that satisfy these sorts of results where ratios of things end up being polynomials even though they shouldn't be.
And maybe, did you have elliptic representation of complex reflection groups?
I mean, that's what this is all about. But
Sorry?
I mean, this paper is about basically. These are all elliptic representations. Yeah.
Okay.
Yeah.
So I have a question. So just given a finite crystallographic complex reflection group, except for this kind of root lattice, there can be more general invariant lattices.
Yeah. So basically, there's two things that happen. One is, there's this crystallographic condition, which means that some of the lattices just don't work. They just don't give you polynomial invariance. But yeah, there can be other crystallographic lattices for some of the groups, especially the non-simply connected groups. I think that's right. But those other lattices, and they all work here. It's just you have to treat them differently because of the different lattice. But right, the way you can think of it is if you look at the D4 case, the invariance for the root lattice there, you basically have, or let's say Dn, you have 4 1s and a bunch of 2s. And then the 2 torsion of that abelian variety, well, the kernel of polarization acts sort of entirely on the 1s. And it acts like the 2 torsion of an elliptic curve. But that means basically what it's doing is it's negating 2 of the invariants and leaving 2 of them the same. But that group doesn't have polynomial invariance, and that linear group doesn't have polynomial invariance. So you basically can easily write down lattices that don't work for this sort of construction. But it turns out that it's always basically given by this crystallographic condition. So basically, in those cases, the extra translations don't show up you can't get them just by using the reflections. They're sort of thrown in additionally on top of all the reflections. But what part of the theory I use for the classification is that you basically, there is a natural lattice in the picture, right? A natural A plus, which is basically, okay, in the complex cases, what is the subgroup generated by reflections? And you can describe that as basically, it's the abelian variety that's sort of generated by the E's, the different copies of E that show up. And then that's sort of the thing that needs to be, well, in most of the cases, needs to be A. And it turns out, it actually is in all cases A. Proving that in the cases where you don't fix the identity is by case, but basically, yeah, that's what's going on. So yeah, it's just, but also you can see that with, already in the torus case, if you take the adjoint group and look at its character ring, it's not generated by the fundamental characters. It's more complicated.
Other questions?
Some time ago, I have described the extension of elliptic hypergeometric series, which I call rarefied. It involves some additional discrete groups in.
Okay.
Can you point where such type of objects live in your scheme?
Nowhere at the moment.
So you have nowhere at the moment.
I have no idea.
You
Yeah.
can't quite.
This is. I'm just sort of dealing. I mean, at the moment, this is just. You can think of this as a purely algebraic geometric thing. This is sort of. This is the natural setting on which you have reflection groups acting with an elliptic curve in the picture.
Yes, they emerge essentially topologically from passing, say, from S3 to some lens spaces. And therefore you have additional the type of things there. So you don't see for the moment the place.
No. I mean, basically, the thing I don't see is what's the analog of an abelian variety.
Yeah.
Other questions? Okay, let's thank you for a very nice talk. So we have a lunch break, and after lunch, starting at 2 o'clock, there is a poster session. So the posters are placed outside in the foyer here, right?
They're in that room where we have
In the room where we have reception.
where the reception is.
Yes. One information. So that place, which is called the M hall, which is going to be used for poster session this afternoon. We can use this place only till today. From after tomorrow, so we cannot be there. So just please be sure not that
The poster session will be removed from tomorrow, okay.
we have to remove
Or
it.
if you don't, you lose your poster.